Again, welcome. Today is April 1st. This is Physics 4B, and we're doing problems from chapter 28. I mean, 28, I'm sorry, 26. Okay. And we're supposed to do problems today. I would like to at least do 4 problems. So let me see which ones they are. Problem 30, problem 31, problem 32, and hopefully problem 38 also, okay, from the RC circuit. There are more problems that I'm hoping to cover for this chapter. Problem 58, if you guys have a chance to look at it, it's really identical to one of the problem 19 or 29, I don't remember which one had the, yeah, problem 19 that had water inside the, basically a container where a resistor was going through it. Now instead of water for problem 58, you have ice. So you need to know the latent heat of ice. And that is basically what you need to know. And so there will be more problems. I'm thinking at least problem 74, which is actually an interesting problem. And there will be a data problem from this chapter also. So here is the deal. There are 2 issues I'm thinking about it right now, 2 ways of doing this concerning Tuesday of next week versus Thursday of next week. There is a chance that, of course, we have lab this afternoon, so it's very important that everybody attends lab or at least do lab. And those, I know some of you have been a little bit behind on the lab, so you guys need to catch up on those things because there will be more grading this week for the previous labs. So I'm hoping to not, for you guys not to lose points, because lab, as you guys know, is extremely important in terms of the grade. It's a quarter of the overall grade, so you don't want to be working off of the 75 points for your class. Now that's one thing. And what I'm saying about Tuesday of next week is either probably we're going to introduce chapter 27 or chapter, or stick with problems from chapter 26. Finish the problems by Tuesday and do chapter 27 on the on Thursday of next week. So that's where I'm right now looking at it. There are 2 ways of looking at it. I still did not decide 100%. In either case, we will complete the problems from this chapter and we will introduce chapter 27 by next week. Make sense? Okay. So let's continue the problem. So we did 19 and 29, that's all. And we had plenty of discussion on them. Some of these problems probably will do them quick, and some others will spend a little bit more time on them, trying to understand all of their inner workings, basically. Okay, so let me share with you the screen. Okay, so you guys are looking at the screen for where it says chapter 26 problems, correct? Yes, maybe?
Yeah, I see it.
Okay, very good. So, problem 30. Some of these problems are actually a repetition of previous ideas, but that just repetition sometimes can be beneficial too. It's just to reinforce the previous stuff, to really understand it better. Because once you see it in a different fashion, it may be even better, okay? So in the circuit shown in this figure 2630, I'm going to draw the figure quickly. Both batteries, and by this time I expect you guys, you have a piece of paper and a pen, and you're ready to write everything as I'm writing, to have a first-hand look at it. You don't want it to really be watching me and then you try to do it later on. No, it's actually good practice that you guys right now grab a piece of paper and pen or a pencil, get to the book if you don't have the book handy actually with you right now. I mean, or go online, download the stuff, basically, the lecture that you need, so that you know exactly what we're talking about. You don't want to watch this. You don't want it to be basically like watching YouTube or anything like that. So we're doing problem 30, and I'm giving you half a minute, basically, more or less, to go and grab your notes, your pen. For those who are here, are you guys ready? You have all of your notes? Yes, no?
Yeah, I got all my pens and paper.
Okay. How about the others? Yes?
Yep, got my tablet all there.
Yes.
Very okay, very good. So okay. So it seems like okay, very good. So now we're going to write. So whatever I do, hopefully you do it and follow through so that we have everything ready for it. Okay, so let's go. So here is the drawing for problem 30. So you might have a pen and paper, so you might have a better drawing than I do. The EMF is 75 volts. There are 3 sig figs in this problem, so it's saying 75.0, so that sometimes is important in terms of that. Especially in terms of the exam that are done online. When I do an exam online, and you will have midterm number 2 online. So pay attention to the class, to the sig figs, please, because I will have them automatically graded in such a way that the sig figs becomes an issue there. So if you put more data in it than necessary, Canvas might give you the wrong credit for it. Or if you give it less precision than what it needs to be, then again, you might lose points in it. So please pay attention to that, okay? Sometimes I override Canvas, but immediately Canvas will give you those grades. We're going to talk about the exam shortly. First of all, you know, guys, that I have 2 sections of Physics 4B of your class. So we will see how we're going to do it, at least online, so that everybody properly tests it. So we have 12 ohms resistor. Okay. And we have a 48 ohm resistor. Okay. And we have also a junction in here where we have a battery in here of an EMF that is unknown. Okay. And the resistor of 15 ohms. And then connect, this is another junction actually. And we have an ammeter in here, A. And connect the whole thing back. Okay. The current is going this way according to the arrow. I don't know if that's the right direction for current or not. Okay. Both batteries have insignificant, so basically they are ideal batteries, significant resistance, and the ammeter is an idealized 1.5 amp in the direction shown is going. So this reads 1.5 amp of current, 1.5 amp going this way on the ammeter. Okay. Find the EMF epsilon, find this one. And the other question is the polarity shown correct? Namely, is this is really the positive terminal and this is the negative terminal of the battery, okay? That means, is this potential higher than this potential? If it is, basically you're good. If it is not, then you're not good. That means the battery is actually backward, okay? So if this point is actually lower, higher potential than this one, then you have to turn at least the drawing backward. So that is what that last question is, the polarity correct or not. So we need to find the EMF. So this is slightly different than the previous problem that we did last time. Let me try to find it. This one also had an unknown EMF. And we're not concerned about the EMF direction because it turns out to be in that direction. But in this case, there might be an issue, okay, with the EMF polarity. Now here is the trick. If you're given a question like this one in any of my exams, do not assume that the answer, just because you're asked about the polarity, that now maybe the polarity is actually backward. So don't go to the last question and say, hey, the polarity probably is in the opposite direction. Do not make that assumption. You really have to calculate things and find if this potential is higher than this potential. That means the polarity is correct. If it is the other way around, that means the polarity is backward. That's all. I know 50% of the time you're going to get it correct just by saying one or the other, which is a gamble. So if at the end you're running out of time, just take that chance. Say one or the other, okay? But technically, you really have to justify your answer. So you really have to, if you're telling me this way or the other, you have to find the potential difference between these points, okay? So the first question first, let's find that EMF first in magnitude. As usual, it's a good idea to put labels. So this junction, I'm going to call it A, lowercase a, and this junction, I'm going to call it B, okay? And I know the current in here is this much. It's 1.5 amps. If I find the current in here, I'm in business. I know exactly how much things are. So if I find the voltage difference between A and B, that is really what that means, that we are in good shape. So I need to find that voltage difference. This current of 1.5 amp is the same current going through this 75 ohms, and it's the same current going through this battery, basically. This resistor, I'm sorry. It's the same 1.5 ohm, 1.5 amp. So I know the difference voltage drop between this point, which now I can label as any point you like, C, for example, okay? The voltage drop between C and A, this voltage drop, the point C is higher than, for the current to flow in this direction, by 12 times 1.5, which is 18 volts, because half of 12 is 6. So there is an 18 volt drop in here. Okay, followed by some drop in here between A and B to make up the voltage drop between C and D to be 75, because this is the voltage drop between C and D, because this is an ideal ammeter. It has no resistance, so there's no drop in between it. So if I think about the problem, I know this voltage drop between A and B. It's 75 minus 18. Since I know the voltage drop across the 48 ohm, and that voltage drop will be just the current times 48. So 48, if I divide 75 minus 18 divided by 48, then I find the current that is going through this one, okay? Or the other direction in here. Because if A is bigger than B, the voltage drop is actually from A to B. If B is higher in potential than A, then the current will be flowing in the opposite direction of the story. Here's the deal. I know it's from A to B. I know A is higher in potential than B because 75 minus 18 is actually positive. So this point A is higher than B. Let's do the math in here to see exactly what's going on, what I'm talking about in here. VA minus VB is equal to VA minus VC plus VC minus VB. VA minus VC is actually negative 18 because C, the current is flowing this way. So the voltage drop between VC and VA is actually 18 volt, is equal to RI, is equal to 1.5 amp times 12 ohm. So this is actually equals to negative 12 ohms times 1.5. And this one, VC minus VB. VC minus VB is actually 75 volt. Because the drop from, I'm coming from the positive in here. I'm saying VC minus VB. The lower end of the battery is always lower in the voltage than the higher end by the amount of the EMF, which is 75, given to be 75. So this voltage drop between A and B is equal to the current that is going through the 48, which I'm going to call it I48. So it's going to be 48 ohms times the current that is going through it in this direction. Because this is positive. 75 minus 18 is what? What is my mathematics? Okay, good. Let me move it to the other side here. 75 minus 12 times 1.2, 1.5, sorry. So it's 57 ohms. So this 57 volts, I'm sorry. So this voltage drop is 57 volts because this is a difference coming from there. So from here, I know what that current is. I-48, the current that is going through the 48 ohms, is going to give me, what, 57 volts divided by 48 ohms, and that is more than 1 amp. Okay, more than 1 ampere. So let's see how much that is. 57 divided by 48. That's 1.1875 amps. Okay. Look, in this junction in here, I know what's going on. In this junction, I have this much current coming, and I have 115 more current going this way. So there must be the difference coming this way. So this current flowing this through this resistor of 15 ohm, and also through the EMF, must be the difference of 1.5 minus 1.1875. Does this make sense that this current in here is, so that when I add this incoming must be equal to the outgoing? Does this make sense to you guys or not? It's very critical because this is the conservation of charge. So the I through 15, I15, must be equal to 1.5 minus this number. 1.5 minus, let me copy it only. 0.3125 amps. I know I'm talking about sig figs and all of that. So this is 0.313 actually, if I want to keep 3 sig figs. But that is a point in here. It's still an intermediary step point because I'm not really finding the actual EMF. The actual EMF will be calculated in here. Okay. Does this make sense so far on how I found that current, I15? So I15 then, because I know that the I15 plus the I48 is equal to 1.5 what this ammeter is reading. Okay, so that means I15 is simply equal to 1.5 minus that 1.1875, which is 0.3125 amps. Make sense?
Yes, it does.
Very good. So now we have the current. Now here is how I calculated VAB. I calculated VAB through point C. Instead, I'm going to introduce a new point in here. I'm going to call it point D. I could calculate it through point D too. I could go this way. Let me show you what I'm talking about. VA minus VB, which I know how much it is. It's 57 volts. I already computed that from the previous calculation. This is how much it is. I know exactly from this calculation how much it is. So this one is equal also to VA minus V, what did I call that one? D, VD plus VD minus VB. I mean, this makes sense. That's exactly how much it's supposed to be. So on one side, VA minus VB, that is the EMF, epsilon. Because the voltage drop from A to B, from A to D, I'm sorry, is the voltage drop across the EMF. So on one side, I know this is epsilon. Plus VD minus VB, that is the voltage drop across a resistor of 15 ohms, that the current going through it is 0.3125 amps. So this is actually equal to 15 ohms times 0.3125 amps. So I know what this number is. I know what this number is. So from here, I'm going to find the voltage cross through the EMF. The epsilon then must be 57 minus this number, 15 times 0.3125. At this point, after I do the calculation, I'm going to use the sig figs. Let's see here how we're going to find that one. So it's going to be 57 minus this number 0.3125, which I don't want to write again. I just want to double click on it, times 15. So it's telling me 52.3 volt. So that is the value of the EMF, and it's a positive number. Had I found it negative, then that means VA minus VD is a negative number. That means the point A sits at a lower potential than the point B, and therefore the EMS have flipped. I found it to be positive. That means A is higher in potential than D, I'm sorry. That means that indeed, this is the proper direction for it. Because the point A is higher than D by 52.3 volts, by this number. So that is the EMF, so the direction of the polarity is correct. Okay, so what's going on in this battery? Batteries normally push current, like this battery is pushing the current of 1.5 amp this way from the positive, and this one is having current flowing in the opposite direction. 0.312 is against it. So this battery is not pushing current, which is 52.3 volt, is having current going through it in the opposite direction from positive to negative. So why is that? It's because there is a bigger battery in the circuit of 57 volts. So this is running current against it, okay? So this is pushing current in the opposite direction. Have you ever jumped a car?
Yeah. So it's essentially charging it is what it is.
Yeah. So if you jump start a car, what do? You plug it into. So it's like you're doing that now. Okay. So we put the positive, and click, and then at the end the thing kicks on, and then you have it. So you have it in the opposite. So the current is actually coming against it. Does this problem make sense to you guys? I don't know. Did we answer all is the polarity? Yes, it's correct. So the fact that they ask it is not really a trick question where you're going to say enter into psychology of thinking. The reason why they ask, and therefore they must have it in mind that the polarity is backward. Therefore, I'm going to choose the polarity to be opposite to what is chosen. And I say, yeah, you're 50% going to have the correct answer if you use this reasoning, except that you're going to get it wrong in this case, because actually the polarity is correct. Good?
Why is it negative 12 times 1.5? Why do we get a negative sign there?
Did I put a negative? Where is it?
Where VA minus VB equals VA minus VC, like a little further down. It was negative 12 ohms times 1.5 amps.
What you're saying in here. Okay, what I'm calculating in here is VA minus VB. Do you see that? Is that what you're talking about?
Yeah,
this number?
Yeah.
Okay, so what I'm calculating in here is VA minus VB, correct?
Yeah.
So what I said, because I don't know how to calculate it in here, because I don't know what the current is. And that's actually the reason why I did that, so that I find that current. Okay, because I know this current is 1.5 amp. So what I said in here is VA minus VB is VA minus VC plus VC minus VB, correct?
Yeah.
So this is perfect. This is, even if you have no idea of what electricity or magnetism is or anything like that, you look at this expression, it's perfect. There is no problem with VA minus VC plus VC minus VB is the same as VA minus. Okay? Now here is the problem. The current is coming down. It's raining from C to A, and you're calculating VA minus VC.
Yeah, I get it. If it was VC minus VA, it'd be positive.
And it's going to be positive. And it's a drop. This one is actually a rise. You're going up. That's what the negative means in here. VA is less than VC. So with the fact that we went against the current is actually minus that number, because this expression is calculating the drop. Since I found A is higher than B, that's why I know this current of I-48 is raining from A to B, because this is actually 57 volt. A and B, there is a gap of 57 volt between them, where A sits higher than B. So that's why the current is coming down from A to B. Make sense?
Yeah, we're all good. I understand now.
Very good, very good. I mean, look, this kind of details can throw you off big time in exams. And I know they may seem kind of obvious at points when you think about them, but they can be confusing when you're doing, especially in a stress amount of time, exam and everything else. They can really, so you really have to be very, very much at ease with this. And that's why practice and practice and practice makes it really more and more obvious. And then hopefully under stress time, you're going to produce these things at ease. Okay. So this is problem 30. Let's tackle problem 31. Problem 31. It says in the circuit shown in the figure, all meters are idealized and the batteries have no appreciable internal resistance. Find the reading of the voltmeter with the switch open. So the first case, they have a switch and they tell you it's open. Which is a higher potential, A or B? So again, we need to find VA minus VB. If it's positive, that means A is higher. If it's negative, that means A is lower than B. That's it. Okay. Find the difference in potential, and that answers that question. Okay. Like, for example, you have two people who live on different buildings, and one of them sits on a floor and the other one sits on a different floor in the same building. But one floor probably is tilted differently than the other one. One of them is probably on the down a hill and the other one is on the uphill. Yeah, maybe you can live on the second floor of this building, but it's higher than the 7th floor of this building because the entire building is tilted. So that's really, as long as if you can find the difference in heights between the two, then you know which one has a higher height than the other one. So which one you can take a rock and throw it will actually fall. Okay, so I'm trying to give an analogy in here. So you have, for example, a mountain hill in here, and somebody lives in this building in the 7th floor. Okay, and somebody lives in here on the 2nd floor only. Obviously, if you take a rock and try to throw it in here, I mean, not throw it up, I mean, drop it. It's not going to reach the 2nd floor on this side. But if you take the same rock and drop it, ultimately it's going to reach the 7th floor here. So all that matters really is how high this point is and how high this point is from some reference. From some reference. It doesn't matter what that reference is. So all we care about is actually the difference in height. That's exactly the same analogy with all of these problems. Okay. So because charges will fall from the high to low. So let's do this problem 31. So let's draw the circuit now. We have quite a few things in here. We have 25-volt battery and a 15-volt battery, and they seem to be actually working with one another now. So we have the positive on one side, the negative on the other, and this is 25-volt battery. We have 100 ohms resistor, and we have a point A. Here it is. And followed by a voltmeter in here, so we're not going to worry about that for right now. And then we have another battery in here. Actually, the polarity is this way. Okay. The positive is pointing down. And we have another resistor now, which is a 75 ohm resistor. And this is point B. Okay. And this point connects to this point, connects to that point. And now we have a voltmeter in here. On top of that, we have a switch in here. I'm going to draw it this way. Right now it's open. And we have an ammeter. Okay. So that's all there is to it. So we want to find the potential difference between A and B. This battery now is 15 volt. It's important. 15 volt. Okay. So the switch S is open. Which point is at a higher potential, VA or A or B? So when it's open. Okay, when it's open, you really don't have this portion at all. So the current will come in from this battery, goes through here, goes through this one, it comes through the whole thing. So as if you really have two batteries. So let's find it. Let's find VA minus VB. First of all, we need this current in here that is going through the circuit, because I have to call somewhere in here. Let's say, for example, this is point C. Okay, if I want to do the algebra, B, and I'm going to call this point between the two D, I'm sorry. So I have A, B, and C, and D, similar to the previous diagram. Here is the thing. I really don't know what that current is. So ideally, I can start from anywhere in the circuit. So I'm going to start from A and come back to A. I know I'm going to get 0 at the end. So VA minus VA is equal to 0. I know that because this is Kirchhoff's rule, actually. And I can go clockwise or counterclockwise, but because I know this direction of the battery is pointing this way, so it's going to push most likely the current in here. So if I assume this direction, and if my assumptions are correct, the current will be positive. As a matter of fact, this battery also is in the same direction, so it's going to push current. So these two batteries will act as a single battery of 40 volt, actually. So as if you have two batteries, basically, and you connected them one end to the other. That's all. I mean, positive to negative and negative to positive. So both of them are pushing current. So you have the positive connected to the negative of the other. So they're actually in series now. So again, this will push the same current in here, and we will have the current flowing through the circuit. So the current in here, because it comes in here, this is a voltmeter. Voltmeters do not, they have a resistance that is infinite. An ammeter has a resistance that is 0. Okay, so there is no voltage drop in here in this ammeter. If it's, the reason why there is nothing in here is because this thing is open right now. And there is an R equal to infinity. So the current that comes in here to the junction A does not go through the voltmeter because it's an R which is infinity. So all the current will come in here and come to this point. There is no current that's going to go in here because R is infinity because of this switch that is open too. When the switch is open, it's acting as an R infinity too. When it's closed is when it acts as an R equal to 0. So now the whole current will go through this just loop. So what we have in this case, it's VA minus, doesn't matter, pick and choose, VD plus VB minus VB plus VB minus VC plus VC minus VA. Okay, let's find the voltage drop, not rise, the voltage drop. Here is a problem. I want from the negative end to the positive end of the 15 volts. So actually, I'm dropping by negative 15 volts. I'm rising because the current is flowing from here. I'm dropping. So I'm sorry. That means I'm rising. So when I say I'm dropping by negative 15, that means I'm rising by 15 volt. That's all. So I'm dropping now. Actually, I'm following the current now by an amount that is 75 times I. I don't know what that I is. Okay, but I should be able to find it. Plus from VB to VC, again, VB is less than VC by 25 volt. So I'm actually rising by 25 volt, or if you wish, I'm dropping by negative 25 volts. It's the same thing as saying I'm rising by 25 volt. I'm dropping by a negative number, okay? Finally, I'm actually dropping from C back to A because C, the current, I chose it in this direction, so it must be dropping. It must be raining from C to A. So in this case, is actually, what is it, 100 times the current I, the same current I by conservation of charge. So this must be equal to 0, where negative 25 and negative 15, it's negative 40 volt. 75 plus 100I, that is 175I. This must be equal to 0 because I started from the same point, I came back to the same point. So this should give me the value of I, that current that I needed, which is 40 over 175, and that should be, should I reduce this number or, I think it's better to keep it in symbolic manipulation. Let me tell you why. I mean, as a fraction, not as a, I'm trying to get my calculator here in my phone because it gives me the fractions better than this thing. This gives me the decimal points, and I really don't want any decimal points. Okay, so what I have in here is I have 40 over 175. Oops, it put 0. 175. 1, not 57, 175. Okay, enter. Come on. You can do it. I should have used the other calculator, which is 8 over 35, okay? 8 over 35. I could probably have found the factors and did that. 8 over 35 amps. That's how much current is flowing through that. The question is, still was not about that. It was asking about A and B. We need to find VA minus VB. That's all. So VA minus VB is the following. You have two ways of finding it. VA minus VB, you could say from the stuff that I have in there, it's VA minus VD plus VD minus VB. So it's VA minus VD plus VD minus VA. This one, again, is a rise by 15 volts because I'm coming from the negative end and going up this way. So this is actually a negative 15 volts because I'm finding the drop. If the whole number is positive, then A is higher than B. If the whole number is actually negative, that means that B is higher than A. That's all. Plus, now the drop from D to A, that's 75 times that current. Oh man, I probably 8 divided by 35, that is the current, times 75 ohms. So I have to add these two numbers and see, is this positive or negative? That's all. If it's 0, that means they are the same potential. There is no high, no both of them. You put a rocket, basically it's not going to move anywhere. Okay, you're on the same floor, same level. So we have to do this algebra in here. Did I gain anything by not simplifying there? I think I probably did not. There is a 7 in the denominator. Okay. So yeah, I don't think I did. So I have negative 15. That is the voltage drop across the battery, which is an actually rise. Okay, I am dropping by negative 15. It's like I'm going down by negative 15, which is I'm really going up by 15. So plus now 75 ohms times 8 over 35. So it's a positive number. It's actually a positive 2.14 volts. Okay, 2.14 volts. That means A is higher than B. Okay, A is higher than B. Okay. Technically, if it were only for the battery alone by itself, if this resistor was not there, this would be actually a rise. Point A would be a lower potential than this point. But because now we have this resistor, overall, A, instead of being lower, is higher. Okay, so let's calculate it from the other perspective now. Let's see if we get the same number. Because remember, I told you, I could calculate VA minus VB in a different fashion by going through the point C. We need to make sure that we actually get the same number. So we're going to calculate VA minus VB, but this time around by going through the point C. It's VA minus VC plus VC minus VB. So again, why is this thing in here?
I have a question on the previous one that we did. I see that you have VA minus VD plus VD minus VA. Is it minus VB or is that supposed to be VA?
Yeah, mistake.
Okay.
Mistake.
Thank you very much. Like, shouldn't it be 0 then?
You're very good. Yeah, that's a very good note. Please correct these things, okay? Sometimes I say things and I write something else, and that's. Thank you very much. Okay, so it's VA minus VB. I'm calculating it. This is for me to check to make sure that I'm getting the 2.14 volt because I got it from going through the point D, and I found it to be 2.14. I said this, if I go this way, it's going to be the same answer. So let's see it. Now I'm going from VA to VB against the current. So it's going to be negative 100 times the current, whatever that current is, which is 8 over 35, okay? But then I'm actually going to go from positive to negative now. So it's going to be pure 25. So I'm actually dropping from VC to VD. I'm actually dropping. And like in here, where I went from negative to positive, in which case I was actually rising. So I said it's a negative drop. In here, it's an actual drop from positive to negative. So my calculation in here is VA minus VC is actually going to be from lower potential A to higher potential C. So in this case, it's going to be a negative 100 ohms times that same current of 8/35 plus 25 volt, because 25 volt is an actual drop now. I'm coming in here. So let's see here if we can get the same correct answer. So I'm going to use a calculator on computer on screen now. It's going to be the same thing anyway, because there is no points in it. So negative 100 times 8/35 plus 25. And the answer is absolutely the same thing. And that is very important. Actually, all the sig figs also, which is positive. So this is just to check. It checks. Okay. So you have options in here when it comes to this kind of situations. Since you already found the current, so you could do it this way and you find an answer just to make sure so that everything is immaculate. You're going to go the other way. The only thing you have to keep in mind is that the current is flowing this way, the one that you found, and you're going from A to B, from A to C. You're going against it now. So you're actually increasing in potential. So it's your negative dropping. You're negative, you're basically not dropping. That's what the negative in here. It's the negation of dropping, okay? Because you're against the current. So it's going to be negative 100 times 8/35. But in actual in here, from here, you're going from positive to negative. That's actually a natural drop. So you put the number as is. As opposed to here, where we're going from negative to positive, we're saying actually we are not dropping by 15 volts. So we put a negative 15 in there. Plus an actual drop in here because the current is going this way. So we're going to actually from D to B. So we're actually dropping. So in this case, we're going 75 times that current that is flowing the circuit. So point A is higher than point B in either way by the same amount. Does this question make sense to you guys? Good?
Yeah, I just think the only like tricky part, if that were to be the word, is from VA minus VD since it's negative 15. But the other one does make sense of it being negative 100 since we're going against the current.
Yeah, and actually the same thing in here, the same situation. Actually, it's the same discussion flipped backward, that's all. The only reason why it's a negative in here because you're coming from less potential to a higher potential. So you're actually dropping. Actually, you're not dropping. I mean, what I'm saying in here is the negation in here, I mean, not the logical negation. How should I say it? It's the negative, basically, of a drop. Because if you're not dropping by 15, it could be dropping by 16, for example. That's not the question in here. What I'm saying in here is the opposite of dropping by 15. So you're rising by 15. Okay. So that's the only thing you have to be careful. And actually in here, going from C to B, you're actually dropping by 25 volt. You're going from positive to negative. So it makes sense to you guys in here that you're dropping by 25 in here. So that it should make sense to you in here that you're dropping by negative 15. Okay? Because you're coming from negative to positive and here going from positive to negative. Both of them yield the same answer though. Good? Byron, we're going to say something?
Oh, yeah, I was just going to say I'm all good here.
Very good, very good. So now with S closed, find the reading of the voltmeter and the ammeter. Which way, up or down, does the current flow through the switch? Now we have a different situation. Okay, so let me draw this thing now. We have basically the switch is closed now. So we actually have a junction in here. So we have an I1 that is going to come from here. Okay. But because there is zero resistance in here, all of this current will flow here. So this is the I100. It's going to come from the 25 battery, goes through the 100 ohm, and come in here. because there is zero resistance in here. So zero resistance will win over. So because there is zero resistance between this point and this point, VAB is equal to 0 now. So in other words, the points A and B will be at the same potential when you close the switch. VA is equal to VB, 1 S closed. Period. Because of the fact that there is no resistance in here, so you're asking me to find what is VA minus VB now. I could calculate it in here and start to think hard and all of that. That you don't need to do that. You don't need to calculate it that way at all. This voltmeter will read 0 because of the fact that this point is A and this point is B. So I can calculate it in here. Actually, there is zero resistance in here. No matter what current you have in there, it's 0 voltage. There is 0 resistance in here, so it's 0. So no matter which current is flowing through this one, so the points A and B become identical. So immediately the reading of the voltmeter will read 0 volts. Okay. Basically, you take 2 wires and you connect them with one another. Where is my voltmeter? It's somewhere hidden in here. Okay. Connect them with one another, and that's it. Their voltmeter will give you 0 volt. Okay. So we know that. The question is, what is the current that is going to be flowing in here? Well, you have an I100 being pushed this way, and it's coming straight through this. In addition, you have another current that is coming from the other battery that is pushing this way. So this is pushing a current, and it finds also 0 resistance in here, so it's going to flow this way. So this is the I75, and the other one is an I100. Which way? How much, first of all, the ammeter will read is going to read the difference between them. Which way it's going to swing, left or right, also depends on which way is stronger, that's all. So we need to find the I100 and we need to find the I red. So I'm going to take this loop in here. This is the direction of the current, so I'm in good shape. This is the direction of the current, so I'm in good shape. So I'm going to take both of them clockwise. So I'm going to go through the first loop. I'm going to start from A to A, it's 0. But I'm going to go through C though, for this loop. So the first one gives me VA minus VB, which is 0. I know that because now the whole thing is short-circuited by that switch being closed, is equal to VA minus VC plus VC minus VB. Okay, and VA minus VC, I'm against the 100 amp now. I mean the I100 now. I'm going VA, which is this whole point. This whole thing is VA, by the way, minus this potential. So it's going to be minus 100 times I. Minus 100 times I plus VC minus VB. That's going to be the entire 25 volt. Because I'm coming from the positive now. So this is an actual drop of 25 volts. So from here, equal to 0, because the points now have been short-circuited. So from here, we're going to find the current I to be simply equal to 25 over 100. And this is easy algebra. I don't need a calculator for it. It's 0.25 amps. So this is how much current is flowing through the 100 ohm the 100 ohm resistor, and this is the red current coming down. So the red current, there is a down current of 0.25 amps. Now let's find the other one, the green one, the I75 current. Okay, we're going to do the same loop now. VA minus VB is still 0 because now they're short-circuited. VA minus VB is equal to 0, which is equal to VA minus VD, I think we called it D, plus VD minus VB. This one, we're dropping by still negative 15 because we're actually rising, okay? So we're dropping by negative 15 volts, plus now we're actually dropping from D to B by this current, which we don't know its value, I75 times the 75 ohms. So 75 times I, 75. This must be equal to 0 because now the 2 points have been short-circuited. This gives me an equation for the current that is running through it, which is 15 over 75. And 15 over 75 is what? Probably I should use it as, no, actually it's good. No, it's 0.2 amps. So here is the story as far as this ammeter is concerned. It's seeing 0.25 amps coming down, and it's seeing 0.2 amps going up. So how much current is going? When you have 0.25 coming down and 0.2 only going up. So what is the net current that is going through it now? What is it going to be?
Wouldn't it just be 0.45?
One of them is coming down, the other one is going up. You see them?
Okay.
So what should we do?
So you
Add or
just subtract them.
Okay. So actually it's going to be I100 because it's coming down, and the other one is going up, I75. And this is going to be 0.005 amps. So that is what that ammeter is going to record. That is what's going to register. Okay. That's going to read this much current through it. Which way, up or down, does the current flow through the switch? Which way do you think it's going to go? Is the current going to come down or going to go up? Knowing that there is 0.25 coming down and 0.2 going up. So is it going to be coming down from this point to this point or up? Here is the situation. I have 0.25 coming down and 0.2 going up. So is the net going down or up?
So it's going down by that amount of 0.05?
Yes. Yeah, that answers the question. Everybody's good?
Yes.
Very good. Hey guys, listen. These things are they are very important. So the reason why I'm saying that is because you'll have stuff that you have to figure out on your own, and think about what's going on. The thing in here that really you need to think hard about it is, what do they mean by an ideal ammeter? It has zero resistance. An ideal switch also has zero resistance. An ideal wire has zero resistance. So no matter what current is flowing through this wire, it has a zero voltage across it. So the minute they said that we close the circuit, and there is no other thing in here, there is no resistor or anything like that to worry about the stuff, then the voltage drop between A and B is zero. That means A and B are exactly at the same height at this point. So this battery is doing its own thing in this portion of the circuit. This battery is doing its own thing around this circuit. Nothing is happening through the voltmeter because it has an infinite resistor. It's an ideal voltmeter. So in this case, the voltmeter will register the reading between A and B, which is this reading, which is 0 volts. So this is easy. So that's part of the question that they asked in here. What is the reading of both the voltmeter and the ammeter? The voltmeter and the ammeter, both of them, one of them will register 0 volt, and the other one will register 0.2 amps. And that to 0.2 amps is coming down from A to B. Okay, so that answers this problem. Good. Problem 32, I think that's probably going to be enough for today if we can get to that problem with enough discussion. Okay. It's kind of dozy problem, kind of a nice problem. So problem 32, it says in the circuit shown, and I'm going to draw a big circuit in here. So I'm hoping you guys are following with your papers and doing all of these things and having good time with these things. So problem 32. It says in the circuit shown, and it shows you a complicated circuit now that has 1, 2, 3, 4, 5, 6, 7, 8 resistors, and it has 2 batteries, and it has an ammeter in it. Okay. The 6 ohm resistor, I'm going to draw it to show you which one is the energy, consuming energy at the rate of 20 joules per second, or 24 watts basically, when the current through it flows as shown. So the current is going up actually from the battery of 25 volts. Find the current through the ammeter A. Wow, that's not... Okay, so we need to find the current through the ammeter A. So let me redraw the circuit because it's quite involved, that circuit, okay? So let's see here. We have a battery in here first that is oriented this way with an EMF that we don't even know what it is. And we have a 17 ohm resistor. And we have that famous 6 ohm resistor that we know a lot about it. First of all, we know the power, and the power, which is Ri squared, is equal to 24 watts. Okay, and the direction of the current through it is this way. So this is the I6 on it. Okay, we only know its direction, we don't know its value yet, so we should be able to get its value. Okay, it's this same current, by the way, because that's the rate at which this energy is. So we should be able to find 24 divided by 6 under the square root. That should be I6. So we should be able to find it right away from the algebra. And in here we have a battery of 24 volts. And we also have a 3 ohm resistor. That 3 ohm resistor must have the same current because this is the same branch. And the same branch carries the same current. So this is also I6. Whatever current in here, we're going to have it there too. Okay. And now we have 13 ohm resistor. And these two are connected in this loop. Now we have another loop on the other side where we have 1 ohm, first of all, sitting by itself in here. And we have an ammeter. Okay. And we have a 19 ohm resistor. And we have actually in here 2 resistors that one of them is 20 ohms and the other one is also 20 ohms. Please do not be intimidated by this kind of problems. They are only just trying to scare you, okay? They are actually very, very easy. As a matter of fact, those two 20 ohm resistors, they're just basically the equivalent of just one resistor, because this is 1 over 20 plus 1 over 20 inverted. So this is as if I have 1 over 20 plus 1 over 20 to the negative 1. And 1 over 20 plus 1 over 20 is actually 1 over 10. When I invert that, it's going to be 10 ohm. So these 2 resistors are actually equivalent to 1 resistor that is just 10 ohm. Okay, when I put them in parallel like this one. So as if it's 10 ohm. So here is the deal. If we find I6, I'm going to start labeling things again. I'm going to call this point A and this point B to make life easy on myself. So I'm going to find the voltage drop between A and B. Once I find the voltage drop, that is the same voltage drop actually between those 2 resistors, which were in parallel. Now I found their equivalent, and the 19 ohm and actually the 1 ohm. So that also should be able to give me the current through this switch. So Let's call this one I-19 just to make sure that we have things in simple, or I-1. It doesn't matter in this case what we call it. But at least since it's immediately connected to the I-19, so I'm going to call it I-19 in here just to so that the algebra we have clear things of what's going on. Okay. So we need to find the voltage difference between A and B. If we find it, we can find I-19 because we know clearly the following: VAB, VA minus VB, is on one side. I drew the current in this direction because I'm thinking maybe, with a little bit of hope, that this is actually the direction with which the current is flowing, and it has to be, because the current in here is flowing this way. So let's see here if that's correct, okay? So if that's the direction of the current that is flowing this way, then the voltage drop between A and B should be just the resistance in here of 10 ohms times I-19 plus 19 times I-19 plus 1 times I-19 is the same thing as this voltage drop. So this is basically what that is. You can call them different points if you like. Call this one A prime and B prime and do the voltage drops. But the voltage drop between this point and this point is just 10 times the same current. Okay, so it's going to be 10 times I-19 plus 19 times I-19 plus 1 times I-19, I-19. This is 1 ohm, the last ohm. So this is 1 plus 19, that's 20 plus 10, that's 30 I-19. But I don't know what I don't know what this voltage drop is, so I need to find it. So here is how I'm going to find it. I'm going to call this point now. It's very important to do this, to call this point C and to call this point D, so that I can do it between these 2 points, because I know the current in here. Here is how much the current is actually. I know that the power is equal to R, which is the 6 ohms, by the way. So this is the 6 ohms, times the I through it squared. We know that from previous chapter, from the same chapter, from the last discussions. So this is always true. The power is the resistance. On the resistor, though, it's the resistance times the current squared. So this is equal to 24 watts. That's what they told us. So that means I6 is equal to 24 over 6 under the square root. And 24 over 6, that's 4. Square root of 4 is 2 amps. So the 2 amps is flowing this way, upward. So there is a current in here of 2 amps going this way. Okay, which is the same current in here also, going through the 3 ohms. I forgot to put the name for this. Is it 3 ohms? Yeah, that was 3 ohms. Okay, so I'm going to find VA minus VB that way. Okay, and then plug it in the other expression and find that current where we're supposed to have it in the ammeter. So let's find VA minus VB. VA minus VB is the same thing as VA minus VC plus VC minus VD plus VD minus VB. So it's VA minus VC plus VC minus VD plus VD minus VB. So this one, point A must be at a lower potential than C. Okay? That's the reason why the current is flowing this way. It must be less because of the fact that the current is flowing. So C is at a higher potential than A. So if I'm going this way, I'm actually rising in potential, what caused the current to flow in that direction. That's what they said in the book. They said that the current, at least in the problem, is going in this direction as shown. So it's actually C is a higher potential than A. So that means I have to, if I'm going this way, I'm actually rising by 2 times 6, which is negative 18. Negative 12, I'm sorry. 2 times 6 is negative 12. So this is actually negative 6 times 2. Now, from C to D, I'm actually dropping in potential by 24 volts because I'm coming down in here from the positive to negative. So this is actually 24 volts. And from D to B, I'm again against the current. The current is 2 amps. and the resistance is 3 ohms. So I'm actually dropping by 3 times 2. So 6 times 2 is 12. 3 times 2 is 18. I mean, 6 plus 12 is 18. Subtracted from 24, the whole thing is 24 minus 18 is 6 volts. So indeed, A sits at a higher potential than B by 6 volts. So I come back to this expression. Now I can find what I19 is. So I19 is simply this 6 volt, which is VA minus VB, by the way, which is calculated from both sides. This is the same voltage as here, divided by 30. Obviously, 6 has 5 of it, so it's going to be 1/5 of an amp. Or what is it? 0.2 amps. Correct? 6 over 30. Yeah, it's 0.2 amps. Some points in the day you start losing touch with the numbers, and so it's 0.2 amps. So that's how much current actually is going through this one, and this is actually the reading of this one. So this is the answer to the question. How much reading is it? It's going to be 0.2 amps. Okay. So this is a question for this one. I know I try to be very thorough and try to analyze things. Probably some of you already have found the answer quickly. That's fine. But please make sure you have all of the steps correct and understand them, because I want you to understand these things more so than actually doing them. That's why I want to be very systematic with these things too. Okay. Part B. What are the polarity and EMF of the unknown battery? So we want to know the polarity. Remember the polarity that was from a problem before the previous problem turned out to be 52.3 volt, and it was actually in the right direction. Okay, so the polarity was correct in this problem. So is it the same thing in here? So let's see. So we need to find the first of all the EMF. Here's what I'm going to do now. I introduce C and D. Let's introduce the point E and the point F. Okay. So that we can say VA minus VB is the same thing. VA minus VE plus VE minus VF plus VF minus minus VB. Here is the problem though. We need to find this current first. We need to find this current because 2 amps is going up and 0.2 amp is coming here. So there is a 0.2 amp coming in here to this junction. Out of the 0.2 amps, only 2 amp left this way. Okay. So which way the current is flowing first and how much? You can see that we have to have a current flowing this way, number one, because this 2 amp is higher by this one, and it has to be exactly 1.8 amps. Does this make sense to you guys in terms of charge conservation? In other words, in this point in here, we have 2 amps came in, and this current is 0.2 amps. So there is a current in here that needs to leave, which is a difference between the 2 and 0.2. And that is exactly 1.8 amp. Does this make sense to you guys that this current through the I-17 must be 1 amp in this direction?
Yeah.
Okay, in this direction, which is critical too. So the direction matters a lot because that means A is a higher potential than E because the current is going from A to E. So it's very important because 2 amps came in here and you just found out that through the ammeter there was a 0.2 amp going through it. So there must be in here conservation of charge in the point E or the point B. It's the same thing, A or B. And that leads to the same story. A current leaving A and coming back in here to B from this side by an exact amount of 1.8 amps. Okay, so that is very critical. So I-75 now in this direction, the way that we have it, is 1.8 amps. So if I'm calculating VA minus VB again, VA minus VB, which I know it's 6 volts now from this previous step, must be equal to VA minus VE plus VE minus VF plus VF minus VB. This one is actually a positive drop. It's a number that is positive, which is equal to, what is it, 75 resistor there? Yeah, 17 ohms times 1.8. So this is 17 times 1.8 plus VE minus VF. VE minus VF is also a drop in potential, assuming that this direction is correct, okay? Plus epsilon. Plus VF minus VB is actually a drop in potential too. The point F is higher than the point B by 13 times 1.8 because the current is raining from F to B. Therefore, this point must be higher in potential. So this is actually 13 times 1.8. I'm sorry. This 13 times 1.8. So this epsilon must satisfy the condition that 6 volts minus 17 plus 13, I took it as a common factor only, times 1.8. So this epsilon must be equal to 6 minus 17 plus 13, that's 30, times 1.8. Obviously, this number is negative. This was not a drop after all, okay? This was a rise by 48 volts. It was a negative drop, if you wish. So the polarity should have been like this, so that we drop by 48. Okay? Because we found a negative drop. This is a negative drop. Which is the same thing as a rise of 48 volts. So when we went through that direction, when we went through the point E to F, we thought we were dropping, but we were rising actually. The point F is situated as a higher point than point E by 48 volts. So the EMF, we know its value is 48 volts. First of all, the epsilon itself, I mean the magnitude of epsilon is 48 volts, but the battery is backward. Do you see the comparison between this problem and problem 30? Problem 30, we ended up with a positive voltage, so in between the battery's ends, and that was correct. So the polarity was indeed correct. In here, we found the polarity to be backward in a sense that the value has the opposite sign, a negative sign. Therefore, the polarity is actually all along was in the opposite direction. So the question is, find what are the polarity and the EMF of the unknown battery, assuming it is negligible internal resistance. Of course, we did that. Does this answer the question? Do you guys see that? I want you really guys to go through this calculation again. Make sure you convince yourself, because this is what we're saying in here. We know A is higher than B by 6 volts through this analysis that we did in the beginning. VA minus VB is actually turned out to be, through the power, we found the current, we calculated VA minus VB, turns out to be 6 volts. So we know that this point in here is higher than this point by 6 volts. So we said, let's calculate through the other one. I know this point A is higher than the point E for sure, because of the fact that there is a current that must be flowing this way of 1.8 amp, because 2 amp came in here. We calculated in the previous step 0.2 amp going that way. Therefore, there is a 1 amp going this way. So the point A is indeed higher than B, than this point E. Then according to the picture, this point in here should be higher than the point F, which should be higher than the point B. And we can point B, F must be higher. It is higher than B. Actually, we know how much higher it is. It's 13 times 1.8, and this point is higher than point E by actually the 17 times 1.8. If you're curious, trying to see how much 17 times 1.8, 17 times 1.8, this is by 30.6 volts higher. Point A is higher. Point F is higher by 13 times 1.8, by 23.4. 23.4. Obviously, these two numbers, if you add them up, they don't account for the fact that there is only 6 volts higher between A and B. Going from A to B is already 30.6. Going from this point to the other one is 23.4. So now you have to account for the fact that you have a 6 volt in the opposite direction, and the battery flipped around is exactly what needs to be done. Okay, because you're dropping by 30.6. That's what that means. You're dropping by 23.4. That's what that means. Okay, and you must be rising just by an exact amount so that this will be 6 volt. Did I make a mistake in the algebra in here? Everything is correct. Okay. 17 times 1.8. What is the overall drop? 17, that's 30. Yeah, that is 54 volts. And you subtract from it the 6 volt to get exactly the 48 that is needed in here. Does this problem make sense to you guys?
Yeah, it does.
Okay, very good. Here is what the deal, guys, is, and it's very important. We have an exam coming immediately after the spring break. It is no secret you're going to have at least one circuit in those problems. You'll have 4 problems in the exam, in the midterm. One of them at least is going to be from chapters 25, 26, which is this kind of circuit, this kind of stuff, okay? Potentially more. So that is not necessarily the only thing. So that is what you have to be focused on in terms of at least one of the things. The other thing is previous chapters when we were dealing with the electric field and all of the other things that have to do with the electric field, and then the capacitors. Don't forget the capacitors, okay? So this stuff is important. Understanding how to handle this kind of situations is very important. So I'm hoping that you guys spend some time during the preparation for the exam, going through these examples, in mastering them. We still are not done by the examples, by the way. We still have problem 38 that I promised we'll do, problem 47 that we should do, problem 74 which we should do, and problem probably 78 or 79 or something like that, okay? Or 80, one of those problems. Problem 81 deals with another situation which we are not going to probably get into. It has a transistor in there and talks about the gain and all of that thing. We're not going to at least worry too much about it in this class. Look at problem 83, it's a lot of fun. Or even that of 84, and man, it's amazing. Well, we'll see. We'll see what we can do, So maybe Tuesday is going to be lecture for chapter 27 and Thursday is going to be problems, or the other way around. Okay, I will let you know. Okay. We have 25. Good. And we have lab this afternoon. Don't forget, guys, that we have very important lab this afternoon. And take care of all of the assignment, please. Like I said, I sent messages to some of you, and hopefully you're working on the missing assignments so that you guys don't miss on your grade. So let me stop the recording.